Fine adult too.
Yeah.
And if it can't, then that's a poorly produced.
All of it is on these big Bibles.
Well, absolutely. But to do it in a way that it doesn't matter, whether you're an adult or child, to pick up on something is. I appreciate it anyway. I don't watch TV much as it is.
I got like, I have one more at home that I need to steal more.
Okay, let me get some stuff back.
What costs money? What, these are free?
Did you get my email?
Oh.
I sent you a response to.
Oh, yeah. Oh, okay. No, I didn't check.
You gotta
Oh,
go to the website.
yeah, I'll check that. It's just-
Never advocate missing class, but those are important things if you have time to try out.
Okay.
Oops, you gotta keep a hold of your units, man. You're not even married yet, man. At some point, your wife will keep them in her pocket, but for now, don't forget it.
I don't even know, man. It's better than all mine.
Very similarly, somebody out of the town today.
I was at my girlfriend's grandma's party or something that last month.
Especially when the weather gets like this.
If I was over there eating some other stuff, and Grandma comes over, she's like, are you vegetarian? I'm like, are you kidding me? You know me.
That's pretty much it for right now. I'm pretty reasonably caught up on stuff, so I've got stuff online graded as well. So, okay, so
That means you read that super long task report?
I don't think I've seen that one.
What?
When did you submit it?
Last weekend?
Okay, well, I go through the list, and it's a really long list, so I just.
Well, I'll double check, in case.
If I did, then I completely skipped it.
Remember
I
that
don't
one
think
that
I did, though.
that I gave to you that I had to put in the right folder? Like, I'll double check again, but I finished it a while back.
Okay, I just missed it. I was just happy to get caught up with a few. Which is rare. And got caught up in my other class, which was helpful. Exactly. Okay, so we've got some stuff to talk about today. Let me make a quick note of what we're talking about today. So, current and resistance.
I have kind of a conceptual question. Can we start with my question?
Maybe.
So, if current represents, I keep thinking about this thing that you said about how the actual speed of electrons moving through conducting wire is relatively slow, but all we really have is this, how many electrons, because we have amperes, right? And that's a, coulomb per second. But
And divide that by E, and that seems ostensibly like a hell of a lot.
a hell of a lot of electrons moving through, but that doesn't really give you a sense of speed in terms of like a meters per second. That gives you how many electrons flow through this plane in a second.
Yeah.
So, and it's a lot. I mean, if you got 500 milliamps, it's like 3.12 times 10 to the 18th electrons.
Well, the way you have to approach it, and this is not immediately obvious based on anything we've done up to this point. In fact, that's probably a reasonable place to start. So, think about it this way. If I can go this route, it's a little bit kind of not how I was going to set it up. But
Okay, no, you don't have to.
no. I think it doesn't matter. It ends up getting back to essentially the same thing. So we'll take this path and we'll kind of see where it goes. So let's start by making some basic assumptions. So we've got some conductor, and this conductor has a certain charge flow I going through it. Now, if you just if you think sort of holistically, what has to happen, first of all, is whatever charge is flowing in is also charge flowing out. So I'm going to just make a note that this needs to be the case. Now, internally, what is it that's physically producing this charge? And that's sort of key to understanding this. It's not a tube where you're just shooting electrons through. What's happening, and I'll just draw a real simple little okay, so think of those as being atoms in one row as representative of the conductor itself. These things aren't just floating around like a gas. We sometimes talk about it as an electron gas, and at least in the old days they used to. But understand, they're held to their atoms. I mean, this is all of the things being equal to there. It's just they're held very loosely, like a partner in a swinging relationship, essentially. Right? So ultimately, and I'll have to do it from this side, right? Because electrons run backwards from the direction we define the current. So if you have an electron being pushed in here, and the electron goes this way, so again, it's arcs backwards, then it's going to push this electron over, and push this electron, and push this electron, and push this electron. And it's a cascade effect that happens about as close to instantaneous as it can be. So you functionally have this displacement of electrons. Now, to say that it's exactly going right to the next atom is probably maybe a little bit naive, but just think about it as sort of pushing it along. And the degree to which, or the energy that's required, if you will, to push it along depends on, among other things, the relative attraction of the electrons to any particular atom. But for all practical purposes, at all points, you have fundamentally a completely neutral atom all along. So even as the charge is flowing, it's a neutral system. You don't have any excess charge buildup as the flow is happening. So to this end then, we only focus on the ends, what's going in and what's coming out. Now, to think about it carefully then, internally what's going on is each atom in the conductor, or I'll say for now in the path, if it's a conductor, it has a certain amount, it's usually one, it has a certain quantity of free electrons, they call them, or conduction electrons, or carrier charges, if you will. It's how many electrons are held loose enough that they physically can come off. So I'm going to call it a free electron. It's not really free, but because it's held so loosely, it's approximately what it is. So, to this end then, we have a couple different things going on. To begin with, we might figure out how many free electrons per cubic meter might even be present in. So one of our important things just analytically to think about is how do we determine the number of these electrons that can physically move around. So to this end, then we might say, well, if each atom has a certain free electron to begin with, how many atoms are there? So in this particular conductor, how many atoms present? And this is, unfortunately, dependent on physically the size of the conductor. Not particularly useful. So maybe instead of thinking about the number of atoms, since it depends on the amount of conductor there, maybe we look at the density of charge that's available to move. So this is not particularly helpful, but the free electron density, sometimes we call it the charge carrier density. This is a constant if the mass density is constant. So we start there. How many atoms are present? So we figure out how many atoms are present per unit volume. Then what we have to do is figure out how many electrons are free on each particular atom to move. So we might start by looking at mass density. You've seen this one before, which I'll use the letter rho. We're going to use two different rhos here now, one that's a tail to the left and one that'll be a tail to the right to represent the resistivity property of a conductor. And the mass density will be the amount of mass per unit volume associated with any particular conductor. And we can describe the mass that's present as the average mass of one atom times, if you will, the number of atoms that are present per unit volume. So without doing any calculation, what we can say is the number of atoms per unit volume, which would represent the mass density of a particular substance, divided by the average mass. This is going to be directly proportional to the amount of free electron carriers per unit volume, charge density, or conductive charge density, per unit volume. So all fun in the sun, it kind of comes back to chapter 15 or so, or chapter 16, book 212. So this is the atoms, if you will, per unit volume. And take it one. So I think first thing might be just figure out what that is for any particular conductor. So as an example, let's use something like, I don't know. I know one little thing about copper, so we'll use copper. And copper has, the reason I'm using copper is that I know it has, there's about one free electron per atom. Sometimes it's one, it could be two, it could be three, and you have to look it up in a table, figure out what it is. But I'm pretty sure it's one for copper, so we'll just stick to copper. So, to this end then, first thing I want to do is to find the free charge density then what I would want to do is figure out the number of carriers per atom and multiply that by N over V in terms of the number of atoms per unit volume. So for copper, let's note that the density of copper is, you can double check this number, but it's right around 8,900. So, well, maybe it's 89, I want to say 8950, that number's sitting in my head. So we can look that up. So the mass density of copper is about this number. And the average mass of copper, of a copper atom, how do you figure out the average mass of an atom of some element?
Look it up in the periodic table.
Look up the atomic mass in the periodic table. That's the mass in atomic mass units. It's also grams per mole, but I don't give a crap about grams per mole. It's a number of atomic units of mass for one atom. So, look it up. It's, I think it's that's the atomic number. There's a periodic table somewhere in this beast.
There's gotta be.
Somewhere probably in the 40s or the 50s.
Oh.
So,
Yeah.
65
here.
or 63.5.
29
Oh, wait,
is the atomic number.
it's, the nice thing is we all have phones, right?
546.
We can find it, but it's in the textbook too, and I think
got it.
63.54. Thank you, sir.
You might want to correct your density too. It should be like 8920, I think.
Okay, 8920. Sorry. We'll fix that. I should have just looked the darn thing up. I didn't.
That's close enough.
I play fast and loose with the numbers. Okay, so we figure out the average mass by 65 point, I forgot the number already. 63.5, okay. So it's 63.5 AMUs, and we have to multiply that by 1.66 times 10 to the negative 27th kilograms per AMU. So probably 10 to the negative 25th, somewhere around 1 something times 10 to the negative 25th. 2 maybe? 2 times 10 to the negative 25th?
1.05.
Okay, so 1.05 times 10 to the negative 25th kilograms. So that's pretty small. But from this information then, we can figure out that N over V should be mass density divided by the average mass, or 8920 kilograms per cubic meter divided by 1.05 times 10 to the negative 25th kilograms. That'll get rid of the kilograms, and this is per atom, if you will. So it'll give us a number that's in atoms per cubic meter.
8.5 times 10 to the 28.
So this would be atoms per cubic meter. And if we multiply this by 1 free electron per atom, it's going to be about 8.5 times 10 to the 28 carrier electrons or free electrons per cubic meter. We got tons of these here, okay? So when we talk about an ampere of current and all of that charge and all of those electrons involved, understand that in terms of the population of electrons that are free to move, even in a cross-sectional area, we're talking about a relatively small proportion of how many are physically available to move. right off the bat. So it's not like there's just a few electrons and therefore they had to go real fast to keep up this charge flow rate. It's the opposite, actually. For a given amount of charge movement, there's a lot of electrons that are capable of moving. Even if this number drops, this is per cubic meter, so make this 10 to the negative 7th cubic, or yeah, 10 to the negative 7th meters. We're still talking in the mole, give or take, range of electrons. So they're just free to move along. So we're talking about large quantities. So, and again, it's this whole idea that they basically step along, essentially, from one to the next. Now, that doesn't necessarily absolve us of the fact that it could be fast rather than slow. And if nothing else, just to put things in perspective, we did some simple gas estimates, how fast gas particles move in the air. We can assume that they don't move so fast in a solid, though at the same temperature, they got to be moving pretty damn fast as they're vibrating. But you remember in the ballpark what that number was, how fast?
500, 600 meters per second.
Yeah, we're talking really, really fast. So all the stuff that's going on internally, and as I've told you, we're talking 10 orders of magnitude smaller. So again, I'm pointing out another huge contradiction to that statement that I made. So, of all the motion going on, my contention is that it's a really, really tiny amount of the overall movement that's going on internally to begin with. So it's a relatively insignificant effect if you think about it that way. So how might we then sort of continue on and figure out what's happening?
Well, I remember from 2012 when we did those calculations, each individual gas molecule was going about 700 meters per second, but since it kept colliding with others,
Yeah, it doesn't go very far.
Its net was, it's not actually all that fast.
Well,
Like when you added up the actual distance that it was.
the root mean square velocity is
Yeah.
huge, but it's changing direction is the thing.
Mm-hmm.
So yeah, so a gas particle over here may take hours to get over here, but it may not go there. It may go somewhere else altogether.
Yeah.
It requires convection to get large bulk of movement of atoms. So, okay, so we know something about the cubic meter density for the number of charges. Now, let's think about how charge is related to pathway, right? Because we don't care about how much is put this way. We want to know about how it's going through this way, right? We're going to worry about if the electrons, if the net velocity is from one end to the other, or backwards for the actual electrons themselves, then really we want to know what's going on this way. So we got a large population. Think of it as the crowd funneling out of the Moda Center after the Blazers got their gratuitous win in a 6-game series, 5-game series. I'd like to think more than that. But we don't
Come on, man.
So I'm hopefully more, right? They're going to roll off 3 straight now. And
Yeah. Game 7.
I've never been done. These are the days where I'm glad I just.
But why not us?
Why
Not us? Okay, I'm sorry. So, why? That's a Nancy, right? Why? No. Okay, so let's look at, if we look at the charge density, across a certain of the conductor, little cross section. And I might even take a step back and say, by the way, if this is the in and this is the out, I'm going to tie this into something we've seen before. And that's something that we've seen before is when you have fluid flow and it's uniform fluid flow, we have mass density or conserved mass from one side to the other. Okay, so you might start by saying, okay, well, if I've got charge flowing this way and I've got charge coming out this way, then the rate of charge movement should be consistent. So I'm going to say dq dt going in. I'm not going to write it as current. I'm going to write it as dq dt. And then ultimately dq dt coming back out. They better be equal. And is that necessarily the approach I want here? So, pardon me here, I'm just thinking about the best way so I don't go down some weird style route. If you have a uniform, just to keep it simple, doesn't have to be, but if you have a uniform cross-section, along the conductor, then how might we be able to phrase this? My surface area. Then the charge density, which would be the amount of cross-sectional current that physically flows through this thing. Again, it's I, but it's electrons going the other direction, unfortunately. The ratio of I to A this would be what we call the charge density. Or not charge density, excuse me, current density. And this should be constant. If the current and the cross-sectional areas are constant, then the charge density over here is going to be the same as it is on the other side. So we're going to write it this way, just to keep it straight. Now, if we express the current in terms of charge and surface area, then, or not charge and surface area, in terms of charge carriers per unit volume, times the amount of charge per moving electron. Let's do this in 2 steps. I just don't want to screw anything up. So we can write I as dq dt divided by the surface area. Okay. And if we look over a small slab, call call this, let's call a little slab here dr. I can make that slab so small that it's basically one atom thick, if you will. So I'm just saying, I'm passing across one little slab. It doesn't have to be large amounts. So as charge is flowing in, charge is flowing out, it's basically one charge per atom moving across here at a certain rate. So to this end then, I'm going to make sure I put my J in here. Then where does that take us?